Hello there, and welcome to Umber Dreams Archives. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Let your body settle into wherever you are. There's no rush, no urgency, just this quiet space we're about to share. Where in the world are you watching from? A quiet bedroom where the day has finally released you. Perhaps a cozy corner where you've come to let your thoughts slow down. Tonight we're going to explore one of the most remarkable detective stories in all of science, The Last Day of the Dinosaurs. We'll discover how scientists pieced together what happened 66 million years ago, understand the clues hidden in rocks and fossils, and contemplate what that single day meant for the entire course of life on Earth. It's a journey that spans continents and epochs, mysteries and revelations, connecting us to a moment of transformation so profound it shaped the world we live in today. But don't worry, this isn't going to be a sensational disaster story or a parade of catastrophes designed to keep you alert. Instead, we'll move slowly and carefully through the evidence, taking our time with each discovery, each piece of the puzzle. We'll explore the science with wonder rather than fear, the extinction with contemplation rather than alarm. By the end, I think you'll find there's something deeply peaceful about understanding our place in the vast sweep of time, something comforting in knowing that life persists, adapts, and continues. If you enjoy these calm explorations into deep time and cosmic events, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with these quiet hours. So settle in, let your shoulders drop away from your ears, take a slow breath, and another. And let's begin our slow drift through time, back to a day that changed everything. There's nowhere you need to be right now, nothing you need to do, just listen and let the story unfold. The dinosaurs have been waiting 66 million years to tell us what happened. We can take our time hearing it. For most of human history, we didn't know dinosaurs had ever existed at all. The bones were there, of course, buried in rock formations around the world, waiting in patient silence. But until the early 19th century, no one understood what they were looking at. When those first massive fossils emerged from quarries and cliffsides, they sparked more questions than answers. What were these enormous creatures? When did they live? And perhaps most puzzling of all, where did they go? The question of dinosaur extinction became one of the great mysteries of paleontology. Throughout the 19th and much of the 20th century, scientists proposed theory after theory. Perhaps the dinosaurs had grown too large, too specialized, too slow to adapt. Maybe mammals had eaten their eggs. Some suggested they'd simply run out of food, or that the climate had changed too quickly for them to cope. Each theory had its advocates, its evidence, its logical framework, and each theory ultimately left something unexplained. What made the mystery so vexing was the pattern in the rocks. Geologists could see it clearly once they learned to read the layers. Below a certain line in the fossil record, dinosaurs were everywhere, diverse and abundant. The dominant large animals on every continent. Above that line they were simply gone. Not gradually declining, not slowly fading away, but absent, vanished. The boundary was remarkably sharp, geologically speaking. Something had happened, something decisive. But what? This brings us to the late 1970s, to a father and son working together on a puzzle. Luis Alvarez was a physicist, a Nobel Prize winner who had helped develop radar and worked on the Manhattan Project. His son Walter was a geologist, drawn to the mysteries written in stone. Together they were studying a thin layer of clay in Gubbio, Italy, a layer that marked the boundary between the Cretaceous and Paleogene periods, the same boundary where the dinosaurs disappeared. They noticed something unusual about this clay layer. It appeared in rock formations all over the world, always at the same point in time, always marking the same transition. It was as if someone had drawn a line across the entire planet, a single moment frozen in stone. The Alvarezes decided to study it more carefully. They wanted to know how long it had taken to form, this mysterious layer that seemed to mark such a profound change in Earth's history. What they discovered instead would revolutionize our understanding not just of dinosaur extinction, but of how catastrophic change can reshape our entire world. And this discovery leads us naturally to the first concrete clue in solving the mystery. The Alvarez's plan was straightforward, even elegant. They would measure the amount of iridium in the boundary layer. Iridium is a rare element on Earth's surface, most of it having sunk to the core when our planet was young and molten. But it arrives constantly from space, carried by micrometeorites, cosmic dust settling gently down through the atmosphere. It accumulates slowly, predictably. By measuring how much iridium the layer contained, the Alvarezes could calculate how long it took to form. More iridium meant more time. It was meant to be a simple experiment, a straightforward measurement. What they found was anything but simple. The boundary layer contained iridium levels 30 times higher than the rock layers immediately above and below it. 30 times. This wasn't a slow accumulation of cosmic dust. This was something else entirely. The team checked and rechecked their measurements. They tested samples from other locations around the world. Italy, Denmark, New Zealand. Everywhere they looked, the same spike in iridium appeared at exactly the same point in the geological record. The implication was startling. Such a concentration of iridium could only mean one thing. Something from space had struck the Earth. Something massive. When the Alvarezes published their findings in 1980, they proposed that an asteroid approximately 10 kilometers wide had collided with Earth 66 million years ago. The impact would have vaporized the asteroid and vast quantities of Earth's crust, sending a cloud of pulverized rock and asteroid material into the atmosphere. This cloud would have spread around the entire planet, eventually settling as a thin layer rich in iridium, the same layer they'd been studying. The scientific community's response was mixed, to put it gently. Many paleontologists were skeptical. An asteroid impact seemed too simple, too dramatic, too much like science fiction. Surely the extinction of the dinosaurs required a more complex explanation, something gradual and terrestrial. Besides, where was the crater? If an asteroid large enough to cause a global catastrophe had struck Earth, it should have left a scar, something massive and unmistakable. Without a crater, the theory remained just that, a theory. But the iridium was real, measurable, undeniable. And as more scientists began looking for it, they found it everywhere. The boundary layer circled the globe. Whatever had deposited that iridium had been a worldwide event, something that had touched every corner of the planet simultaneously. The layer contained other clues too. Tiny glass spheres called tektites, formed when rock is melted and flung through the air. Shocked quartz, a form of the mineral that only appears under the extreme pressures of impacts or nuclear explosions. Soot, suggesting massive wildfires. Each piece of evidence pointed in the same direction. Something catastrophic had happened 66 million years ago, something that left its signature in the rocks of every continent. The Alvarezes had found their clue, their layer of iridium like a message from deep time. Now scientists around the world began searching for the source, for the place where this cosmic visitor had made its mark. The hunt for the crater was on, and it would lead to one of the most significant geological discoveries of the 20th century. The crater, when they finally identified it, had been hiding in plain sight for decades. Oil prospectors had detected it in the 1950s, working in the Yucatán Peninsula of Mexico. They'd noticed a circular pattern in the subsurface rock, a strange formation centered near the small town of Chicxulub Puerto. The pattern suggested an ancient structure buried beneath younger sediments, but the prospectors were looking for oil, not ancient impacts. They noted the anomaly in their records and moved on. It wasn't until the late 1980s, after the Alvarez's iridium discovery had set scientists searching for a crater, that researchers took another look at those old petroleum surveys. A geophysicist named Alan Hildebrand was studying the impact theory, convinced that if a crater existed, it should be enormous, possibly buried or eroded away. When he learned about the Yucatán structure, he realized he might be looking at the answer. The evidence began to accumulate quickly. The circular feature was massive, over 180 kilometers in diameter. Dating of the rocks showed they had been shocked and melted 66 million years ago, exactly at the boundary between the Cretaceous and Paleogene. The chemistry matched. The timing matched. The size matched what would be expected from an asteroid capable of causing global devastation. This was it. This was ground zero. Chicxulub. The name comes from the Yucatec Maya language, meaning roughly "0" or "1". The ancient Maya who named this place had no idea what lay beneath their feet, what story the rocks could tell. But now, with modern technology, scientists could peer through miles of limestone to see the scar left by the most catastrophic day in the history of life on land. The crater's structure tells its own story. There's a peak ring, a circle of mountains thrust upward by the rebound of rock after the initial compression of impact. There are multiple rings, actually, frozen waves in stone marking how the crust rippled outward from the point of collision. The entire Gulf of Mexico was affected. Rocks in Haiti show signs of having been part of a massive tsunami. Glass spheres ejected from the impact have been found across North America. Drilling into the crater has revealed layers of impact melt. Rock that was liquefied by the violence of the collision, and then cooled and solidified again. Below that, the rock is fractured and shocked, forever altered by pressures that most materials on Earth's surface never experience. And everywhere, at the right depth, there's that telltale layer of iridium, the calling card of an extraterrestrial visitor. Finding Chicxulub transformed the impact theory from hypothesis to established fact. The debate shifted from whether an asteroid had struck Earth to what exactly had happened during and after that impact. Scientists could now focus their questions. How did the extinction actually occur? What were the mechanisms? How long did it take? And perhaps most importantly, what was life like just before everything changed? With the location of the impact established, researchers could work backward and forward in time, reconstructing not just the impact itself, but the world it destroyed and the world that emerged from its ruins. Let's begin by establishing when this happened, by understanding the deep time that separates us from that fateful day. 66 million years. The number is so large it becomes almost abstract, a figure we can recite but struggle to truly comprehend. To put it in perspective, modern humans, Homo sapiens, have existed for perhaps 300,000 years. Recorded human history spans maybe 5,000 years. The entire story of human civilization, from the first cities to the present day, fits into the last eye blink of geological time. The dinosaurs had already been extinct for 65.5 million years before the first human being walked upright. Let's try to grasp this span another way. Imagine you could compress all of Earth's history into a single 24-hour day. Earth forms at midnight. Life appears in the early morning hours. The dinosaurs don't appear until around 11 o'clock at night. They reign for about 3 hours, dominant and diverse, spreading across every landmass. Then, at 10 minutes before midnight, they're gone. Everything that follows, all the mammals rising to prominence, all the ice ages, all of human evolution and history, happens in those final 10 minutes. The impact that created Chicxulub occurred at what geologists call the Cretaceous-Paleogene boundary, often abbreviated as the KPG boundary. The Cretaceous period was the last and longest period of the Mesozoic era, the age of dinosaurs. It had lasted for nearly 80 million years, a span of time so vast that the dinosaurs alive at its beginning would have considered the dinosaurs at its end as unimaginably distant as we consider them now. Dating this boundary precisely has been one of the triumphs of modern geology. Scientists use radiometric dating, measuring the decay of radioactive elements in volcanic rocks formed at the time. The most precise estimates place the impact at 66.016 million years ago, give or take about 50,000 years. That margin of error might seem large, 50,000 years, but in geological terms it's remarkably precise, a near instantaneous moment in the vast flow of time. What's fascinating is how much we can know about this specific point in time. The rocks remember. They remember the angle of the asteroid's approach, coming in from the southeast at about 60 degrees from horizontal. They remember the season, likely spring or early summer in the northern hemisphere, based on the growth patterns of fossil plants and the presence of young dinosaurs. They remember the time of day, which we'll explore shortly. The precision of this knowledge, gleaned from rocks that have witnessed the slow dance of continents, the rise and fall of mountain ranges, is humbling. This moment, 66 million years ago, represents one of the 5 great mass extinctions in Earth's history. About 75% of all species on Earth went extinct. On land, every animal larger than about 25 kilograms died out. In the oceans, the ammonites vanished, along with the great marine reptiles. It was the end of an era in the most literal sense, yet life persisted. In the devastation's wake, new opportunities emerged. The survivors, small and adaptable, would inherit a transformed world. Within a few million years, an eye blink in geological time, the planet was thriving again, though utterly changed. The age of mammals had begun, set in motion by 10 kilometers of rock, travelling through space at 45,000 miles per hour. Understanding this timeline helps us appreciate both the catastrophe and its context. 66 million years ago. The world was already ancient, life already varied and complex, and in the 66 million years since, life has proven itself remarkably resilient, capable of recovering even from planetary-scale disaster. But we're getting ahead of ourselves. Let's return to that day, to the morning when everything changed, and piece together what we can know about those final hours. We can't know the exact date, of course. The Cretaceous calendar didn't align with ours, and the concept of April or any other month would have been meaningless. But based on fossil evidence, particularly the pollen in the boundary layer and the age of juvenile dinosaur specimens found just below it, many scientists believe the impact occurred in what would correspond to spring or early summer in the northern hemisphere. Let's call it an April morning, knowing we're imposing our familiar framework on deep time's mysteries. The day began like any other day in the late Cretaceous. In what would become the Hell Creek Formation of Montana and the Dakotas, the sun rose over a landscape that would seem both familiar and alien to modern eyes. There were rivers, broader and slower than today's, meandering through forested floodplains. The climate was warmer, more humid. Palm trees grew where now there are wheat fields and prairie grass. The air was thick with the sounds of life. Triceratops moved through the undergrowth. 3-horned herbivores the size of elephants, using their powerful beaks to strip vegetation. Tyrannosaurs, the apex predators of their time, perhaps rested in the shade. Conserving energy for the hunt to come, smaller dinosaurs darted between the trees. Pterosaurs soared overhead, their leathery wings catching the warm updrafts. In the nearby ocean, mosasaurs, great marine reptiles, cruised through waters teeming with fish and ammonites. None of them knew what was coming. How could they? The asteroid had been falling toward Earth for millions of years, a dark visitor from the outer solar system, perhaps knocked from the asteroid belt by Jupiter's gravity. It had crossed the orbit of Mars, sailed past the Moon, entered Earth's atmosphere. The entire journey from the moment it became visible in the sky to impact took perhaps a minute, maybe less. Not long enough for any creature to understand what they were seeing, just a brief, bright streak across the morning sky. Recent discoveries have allowed scientists to reconstruct the impact's timing with remarkable precision. In 2019, researchers published findings about a site in North Dakota called Tanis. This fossil deposit contains creatures that appear to have died within minutes or hours of the impact, preserved in such detail that their final moments are still legible in stone. The fish fossils at Tanis have impact spherules in their gills, tiny glass beads formed in the impact's fireball and ejected on ballistic trajectories. The presence of these spherules in the gills suggests the fish were breathing when the spherules fell, which happened within the first hour after impact. The timing of day has also been inferred. The impact created massive seeches, standing waves in bodies of water caused by the ground shaking. The characteristics of these seeches, preserved in the rocks, suggest the impact occurred during daylight hours. Some researchers have proposed it was around mid-morning to early afternoon, when the sun would have been bright in the Yucatán sky, illuminating a shallow, clear sea that had no warning of what was about to strike it. So picture this April morning, 66 million years ago, dinosaurs going about their ancient routines, the sun climbing toward noon, a gentle breeze off the ancient ocean, insects buzzing. Somewhere, perhaps, a clutch of eggs beginning to crack as new life struggled to emerge. Normalcy, routine, the continuation of patterns that had persisted for millions of years. And then, without warning, in an instant too brief to comprehend, everything changed. But to understand how and why, we need to step back further, to understand where this cosmic visitor came from and what it carried with it on its long fall toward Earth. Before it was the object that ended the age of dinosaurs. The Chicxulub impactor was simply a piece of rock drifting through the cold silence of space. Its journey to Earth likely began in the asteroid belt, that broad ring of debris orbiting between Mars and Jupiter, leftovers from the solar system's formation 4.5 billion years ago. For most of its existence, it followed a stable orbit, one of millions of rocky fragments circling the sun in a slow, predictable dance. The asteroid belt isn't the crowded demolition derby often depicted in science fiction. In reality, space between the asteroids is vast, empty. A piece of rock might orbit for billions of years without coming close to another object. But the belt is gravitationally stirred by Jupiter, that giant planet whose mass dominates the outer solar system. Jupiter's gravity creates resonances, zones where asteroids are periodically tugged, their orbits gradually changing over millions of years. Eventually, perhaps tens of millions of years before the impact, one of these resonances nudged the future Chicxulub impactor. Its orbit began to shift, becoming more elliptical, carrying it closer to the sun on each pass. This process takes enormous spans of time. Orbits don't change quickly, not at these scales. But gradually, inexorably, the asteroid's path began to cross the orbital paths of the inner planets. It became what astronomers call a near-Earth object. Still, space is vast and planets are small. The asteroid might have continued in its new orbit indefinitely, passing near Earth countless times without incident. Our planet occupies a tiny fraction of its orbital path. The chances of a collision on any given pass are infinitesimally small, but given enough time, even unlikely events become inevitable, and this asteroid had time, millions of years of time to make its approach. We can estimate its trajectory from the crater it left behind. The impact angle, about 60 degrees from horizontal coming from the southeast, suggests it approached from a particular direction in space. Computer simulations can work backward from this, tracing possible orbital paths. Most likely, it was in a relatively low eccentricity orbit, meaning it wasn't coming in at extreme velocity from the outer solar system. Its speed at impact, approximately 20 kilometers per second, or about 45,000 miles per hour, is consistent with a main belt asteroid on an orbit that had been perturbed into Earth-crossing territory. During its journey through space, the asteroid would have been cold, far colder than anything we experience on Earth. In the asteroid belt, sunlight is weak, temperatures hovering around minus 70 degrees Celsius in the sun, even colder in shadow. The rock would have been ancient, unchanged since the solar system's birth, perhaps bearing the scars of earlier collisions, its surface powdered by micrometeorite impacts into a layer called regolith. And then came the final approach. As it fell toward Earth, the sun growing larger ahead of it, the asteroid would have begun to warm just slightly. It crossed the Moon's orbit. From Earth, if anyone had been watching with instruments capable of detecting it, it would have appeared as a faint point of light, brightening rapidly. In the final hours, it would have become visible to the naked eye, a star where no star should be, growing brighter by the minute. In the last moments before impact, as it plunged into Earth's atmosphere, it would have begun to glow, friction with air molecules heating its surface to incandescence. The sky would have lit up brighter than the sun, and then, travelling at 45,000 miles per hour, carrying the kinetic energy of 100 million megatons of TNT, it struck the shallow sea near what would become the Yucatán Peninsula. Let's consider carefully what this object was, this 10-kilometre wide messenger from the deep past of the solar system. 10 kilometres, 6 miles, about the distance you might drive to run a quick errand, or the length of a morning jog. It seems almost modest when stated that way. But imagine that distance not stretched out in front of you but compressed into a sphere. A single solid object of rock travelling faster than anything in our everyday experience. Imagine standing at one edge and looking across to the other side, trying to see across 6 miles of solid stone. The mass of the Chicxulub impactor is estimated at between 1 and 4 trillion metric tons. That's difficult to conceptualize. Consider that the Great Pyramid of Giza, one of the most massive structures humans have ever built, weighs about 6 million metric tons. The asteroid that killed the dinosaurs had the mass of perhaps 200,000 Great Pyramids, all compressed into a single object. What was it made of? Analysis of the iridium and other elements in the boundary layer suggests it was likely a carbonaceous chondrite, a type of primitive asteroid rich in carbon and water-bearing minerals. These are among the oldest, least altered objects in the solar system, time capsules from the era when planets were forming. The asteroid that struck Earth had probably looked much the same for 4.5 billion years, a dark, roughly spherical mass of ancient rock and metal. The composition matters because it affected what happened during the impact. Carbonaceous chondrites vaporize more readily than iron-rich asteroids. When this object struck, it didn't so much crash as explode, converted from solid matter to superheated gas in milliseconds. Everything it was made of, all trillion tons of it, was blasted into the atmosphere as vapor and tiny particles. This is why we find the iridium layer worldwide. The asteroid became part of the global dust cloud. The size also matters enormously. An asteroid 1 kilometre wide would have caused regional devastation, but not global catastrophe. An asteroid 100 kilometres wide would have caused an extinction so severe that complex life might not have recovered. 10 kilometres was, in a terrible sense, perfectly sized to radically transform the planet without sterilizing it entirely. It was large enough to inject massive quantities of debris into the atmosphere, blocking sunlight for months or years, but not so large that it would have boiled the oceans or stripped away the atmosphere entirely. Consider the kinetic energy involved. Energy equals 1/2 mass times velocity squared. The Chicxulub impactor, travelling at 20 kilometers per second, carried kinetic energy equivalent to about 100 million megatons of TNT. The largest nuclear weapon ever detonated, the Soviet Union's Tsar bomber, released 50 megatons. The Chicxulub impact released energy equal to 2 million Tsar bombers exploding simultaneously. The largest earthquake ever recorded, the 1960 Chile earthquake, released about 1/2000th of the impact's energy. This wasn't merely an explosion. This was enough energy to instantly vaporize thousands of cubic kilometers of rock, to send shockwaves through the entire planet that registered on seismographs on the opposite side of the globe, to generate heat so intense it set forests aflame thousands of miles away. The impact excavated the crater in seconds, throwing up a curtain of material that briefly reached into space before falling back to Earth. Yet for all its violence, the impactor itself was just a piece of rock. It had no malevolence, no intent. It was simply following the laws of physics, responding to gravity, falling along the path those laws dictated. It had probably collided with Earth before, or rather, Earth had collided with it billions of years ago during the planet's formation. The material that makes up the asteroid likely came from the same nebula that formed Earth. In a sense, this was a reunion, cosmic matter that had been separated for eons coming back together in the most violent way possible. The random nature of the impact is worth contemplating. If the asteroid had arrived 15 minutes earlier or later, it might have struck open ocean instead of the shallow Yucatán Sea. The effects would have been different. If it had arrived a few million years earlier, different species would have been dominant. A few million years later, the dinosaurs might have already been in decline from other causes. The exact moment of impact, the exact location, shaped the entire future of life on Earth. And that moment, that location, were entirely matters of chance. Of orbital mechanics and gravitational perturbations playing out over millions of years. This piece of rock, unremarkable among countless others in the asteroid belt, became the object that reshaped our planet. And it struck in a very particular place, a location that would amplify its effects. Let's turn now to where it hit, to the Yucatán Peninsula as it exists today, and what lies buried beneath those tropical forests and tourist beaches. If you visit the Yucatán Peninsula today, you'll find a landscape of startling beauty and apparent tranquility. White sand beaches curve along turquoise waters, Mayan ruins rise from the jungle, pyramids that seem ancient until you remember they were built 65 million years after the impact. The town of Chicxulub Puerto sits peacefully on the coast. Its name the only obvious hint of what lies beneath. You could stand at ground zero and never know it. The crater itself is invisible from the surface. After 66 million years, newer rocks have covered it completely. Limestone deposited by the shallow seas that covered the region for much of the time since the impact buries the crater under hundreds of meters of younger rock. The coastline has shifted, the rivers have moved, the landscape has been completely transformed by time. Only with sensitive gravity measurements and magnetic surveys can the circular structure be detected, a ghost beneath the ground. But the crater is still there, preserved in the deep rock. Drilling projects have brought up cores from various points within the structure. Physical samples of impact melt and shocked rock. These cores tell a remarkable story. The rock shows evidence of having been liquefied and then rapidly cooled. Quartz grains contain microscopic fracture patterns that only form under extreme pressure. Feldspar crystals show signs of having been partially melted. The rock remembers. The Yucatán at the time of impact was very different from today. It was covered by a shallow sea, perhaps a few hundred meters deep. Warm and clear. Below the water sat a thick platform of limestone, the accumulated shells and skeletons of countless marine organisms deposited over millions of years. This limestone would play a significant role in the impact's effects. When vaporized by the heat of the collision, it released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere, adding to the catastrophe. Today the region is characterized by cenotes, natural sinkholes that form when limestone caves collapse. These cenotes are scattered across the Yucatán, and they're not randomly distributed. Many of them form a ring, roughly aligned with the edge of the buried crater. The impact fractured the limestone in circular patterns, creating zones of weakness that, over millions of years, allowed water to dissolve the rock and form caves. When the caves grew large enough, their roofs collapsed, creating cenotes. The ancient Maya considered these cenotes sacred, using them as sources of fresh water and, sometimes for ritual purposes. They didn't know they were swimming in water that flowed through rock fractured by the impact that ended the age of dinosaurs. The peninsula's ecology today bears no relationship to what existed before the impact. The tropical forests, the jaguars and howler monkeys, the parrots and butterflies, all evolved in the world that came after. The dinosaurs that once roamed here are gone, so completely that they left barely a trace. A few fossils have been found in Mexico from the late Cretaceous, but they're rare. Most of what we know about the dinosaurs that lived in this region comes from better preserved fossil beds elsewhere. Standing in the Yucatán today, in the warm sunshine, listening to the waves lap against the shore, it's hard to imagine this as the site of Earth's greatest catastrophe. The planet has healed. Life has returned, diverse and abundant. The forests are thick. The reefs offshore are vibrant with life. Millions of years have softened every scar, buried every trace of that terrible day. Yet the impact's legacy persists in subtle ways. The chalk deposits of Europe, including the famous White Cliffs of Dover, were forming at the time of the impact. The KPG boundary can be found there, a thin, dark layer in otherwise pristine white chalk. The boundary exists in rocks on every continent, in sediments at the bottom of the ocean, even in ice cores from Antarctica. The impact didn't just affect the Yucatán, it touched the entire planet, leaving its signature everywhere. The peaceful landscape of today's Yucatán is a testament to time's healing power, to life's resilience. But it also reminds us how little we can read from surface appearances. Beneath our feet lies history, deep and consequential, invisible but real. The rocks hold memories that span unimaginable time, and if we learn to read them, they tell us stories of a planet far more dynamic, far more dramatic than we might otherwise imagine. Before we witness what happened at the moment of impact, let's step back one more time and meet the creatures who were living their lives on that April morning, the dinosaurs in all their diversity and magnificence. The late Cretaceous world was crowded with life, more diverse and specialized than at any previous point in the Mesozoic era. Dinosaurs had been evolving for over 150 million years by the time of the impact. They had filled nearly every ecological niche on land, from tiny insectivores the size of mice to the most massive land animals ever to walk the earth. They were successful beyond measure, and they had no reason to expect that success would ever end. In North America, Tyrannosaurus rex was the apex predator, possibly the largest terrestrial carnivore that has ever existed. Adults could reach 13 meters in length and weigh as much as 9 tons. Their teeth, some as long as bananas, could crush bone. Their jaws generated bite forces that exceeded anything known in the modern world. They were ambush hunters, using their keen vision and sense of smell to locate prey, then relying on powerful legs to close the distance in a short, devastating burst of speed. Their primary prey included the ceratopsians, the horned dinosaurs. Triceratops was the most common, abundant in the fossil record of the latest Cretaceous. These animals travelled in herds, using their elaborate frills and horns for display, combat with rivals and defence against predators. They were herbivores, but formidable ones, capable of inflicting terrible damage on any predator foolish enough to attack an adult head-on. Their beaks could slice through tough vegetation, and their batteries of teeth, hundreds of them constantly being replaced, could grind down the most fibrous plants. The hadrosaurs, or duck-billed dinosaurs, were even more diverse. Edmontosaurus, one of the largest, could reach up to 12 meters in length. These were the cattle of the Cretaceous, social herbivores that moved in large herds, probably migrating seasonally to follow food sources. Some hadrosaurs had elaborate crests on their heads, hollow structures connected to their nasal passages. These may have been used for vocalization, allowing individuals to signal across long distances, maintaining herd cohesion in dense forests or across broad floodplains. Smaller dinosaurs filled the underbrush. Ornithomimids, looking remarkably like modern flightless birds, darted through the vegetation on long legs. Troodontids, small predators with large brains and keen eyesight, hunted by night. Ankylosaurs, armoured herbivores covered in bony plates and wielding heavy club-like tails, browsed on low vegetation. The diversity was staggering. Each species adapted to its particular way of life. In the southern continents, the fauna was different but equally diverse. South America hosted massive titanosaurs, long-necked sauropods that could reach 30 meters in length. Argentinosaurus, one of the largest dinosaurs ever discovered, may have weighed as much as 90 tons. These giants had no predators capable of killing a healthy adult, though young individuals were vulnerable. The predators they faced included the abelisaurids, stocky carnivores with short, deep skulls and tiny arms, quite unlike their northern cousins. The skies were ruled by pterosaurs, not dinosaurs but close relatives. The late Cretaceous saw the evolution of the largest flying animals ever to exist. Quetzalcoatlus had a wingspan approaching 10 meters, larger than a small airplane. Despite their size, these animals were remarkably light, their bones hollow and thin-walled, their bodies covered in a coat of fine fibres similar to fur. They soared on warm updrafts, scanning the ground for carrion or small prey. In the oceans, life was equally diverse. Mosasaurs, giant marine reptiles related to modern monitor lizards, ruled the seas. Some reached lengths of 17 meters, with powerful tails for propulsion and jaws lined with sharp teeth for catching fish and other marine reptiles. They shared the oceans with plesiosaurs, long-necked or short-necked forms, all specialized for hunting in the marine environment. Ammonites, shelled cephalopods related to modern nautilus and squid, filled countless niches, ranging from tiny forms no larger than a coin to giants with shells 2 meters across. This was a world in balance, ecosystems that had been established for millions of years. Predators and prey had co-evolved, each pushing the other toward greater specialization. Plants and herbivores existed in equilibrium, with flowering plants becoming increasingly dominant throughout the Cretaceous. Insects, particularly pollinators like bees and butterflies, had co-evolved with these flowering plants. Birds, descendants of earlier dinosaurs, occupied niches in the trees and skies. Mammals existed but were mostly small, occupying nocturnal niches where they could avoid competition with the dominant dinosaurs. It's important to understand this diversity, this success, to fully appreciate what was lost. The dinosaurs weren't failing when the asteroid struck. They weren't in decline, weren't gradually being replaced by more efficient mammals. They were thriving, diverse, specialized, and abundant. Their extinction wasn't the result of any inadequacy on their part. It was simply catastrophically bad luck, being in the wrong place at the wrong time, existing on a planet when a rock from space happened to fall, and on that April morning they were simply going about their lives, unaware that normalcy itself was about to end. Imagine for a moment a triceratops in what is now Montana. She's been awake since just before dawn, when the first light began filtering through the forest canopy. She's hungry, as she usually is. A 3-ton herbivore requires enormous amounts of food. She browses on low shrubs, using her beak to clip off branches, then grinding them with her batteries of teeth. The taste is familiar, comforting. This is what she does, what her ancestors have done for millions of generations. Nearby, a young Edmontosaurus separated from its herd calls out a low, mournful sound produced by air resonating through its elaborate head crest. The sound carries far in the still morning air. Somewhere, hopefully not too far away, the herd will hear and answer. Being alone is dangerous. There are predators here, patient and clever. In a clearing a few miles away, a Tyrannosaurus stirs. She's been resting, conserving energy, digesting her last meal from 3 days ago. But hunger is beginning to motivate her again. She rises slowly for an animal her size and begins to move through the forest. Her eyesight is excellent, better than an eagle's. She can see movement, detect the slightest disturbance in the normal pattern of the forest. She's looking for young, old, or injured animals. Healthy adults are too dangerous to attack without certainty of success. In the canopy above, a pterosaur glides between trees, searching for insects disturbed by the larger animals below. Its keen eyes spot a beetle, and it folds its wings slightly, dropping down to snatch the prey in its beak without landing. The beetle is consumed in flight. Life continues. The sun climbs higher. In the shallow sea that covers the Yucatán, A mosasaur swims lazily through the warm water. The sea is clear, almost perfectly transparent. The bottom is visible far below, a landscape of rippled sand and scattered shells. Small fish scatter at the mosasaur's approach, a constant rain of silver in the sunlight filtering down through the water. The marine reptile isn't particularly hungry at the moment. It's just swimming, enjoying the warmth, existing in a state that might be called contentment if we could know the inner life of such a creature. On the sea floor, ammonites crawl slowly over the sand, leaving delicate trails behind them. These shelled cephalopods have existed for hundreds of millions of years, surviving multiple smaller extinction events. Their diversity is astounding. Thousands of species filling every marine niche from the shallows to the deep ocean. They have no reason to believe this day is any different from any other. Back on land, the Triceratops has found a patch of particularly tender ferns. She settles in to feed in earnest, her head moving rhythmically as she clips and chews. The sunlight is warm on her back. Insects buzz around her, drawn by her scent and by the sap from the plants she's crushing. Some land on her frill, walking across the bony surface. She flicks her head occasionally, dislodging them, but it's more reflex than annoyance. High above in the atmosphere, something appears that hasn't been there for millions of years. A tiny point of light, brighter than any star, visible even in the daytime sky. It's growing brighter by the second. No creature on Earth has the capacity to understand what it means. No brain on the planet can process what's about to happen. The object has been falling toward this moment for millions of years, following laws of gravity and motion that care nothing for the life that has flourished on this planet, that has no preference for one outcome over another. The Triceratops continues eating. The Tyrannosaurus continues hunting. The mosasaur continues swimming. The ammonites continue crawling. The pterosaur continues gliding. All around the world, in every ecosystem, in every niche, life continues in its ancient patterns. There's no sense of foreboding, no animal intuition warning of catastrophe. Why would there be? Nothing in the evolutionary history of any of these species has prepared them for what's coming. Nothing could prepare them. The last normal moments tick by. The asteroid now so close that if the Triceratops could understand such things and looked up at just the right moment, she might see it as more than a point of light, as an actual object growing larger in the sky. But she doesn't look up. She keeps eating. The ferns are particularly good here, and she's had a good life as dinosaur lives go. She's survived to adulthood, avoided predators, found enough food. She's nested several times, laid eggs that hatched, seen some of her young survive to independence. In evolutionary terms, she's been successful. Her genes will continue, carried by her offspring into the future, except they won't, because in just a few minutes, everything will change. The future she assumes exists, the continuation of patterns that have persisted for so long they seem eternal, that future is about to be erased. Not gradually, not with warning, but instantly, violently, completely. The last normal morning of the age of dinosaurs is ending. The final seconds are ticking away, and then, above the Yucatán, the sky begins to burn. The asteroid strikes the shallow sea at 20 kilometers per second, roughly 60 times the speed of sound in air. What happens in the next second defies any normal understanding of physical processes. The energies involved, the pressures generated, the temperatures reached, all exceed anything that occurs naturally on Earth's surface. This is cosmic violence, the kind of event that shapes planets. At the moment of contact, the front of the asteroid begins to compress. Rock doesn't have time to behave like rock at these speeds. It acts more like a fluid, or even a gas. The tremendous kinetic energy converts to heat almost instantly. The surface of the asteroid reaches temperatures of several thousand degrees in the first microseconds. The water and rock it's striking aren't pushed aside so much as vaporized, converted from liquid and solid directly to superheated gas. The asteroid continues downward, ploughing into the bedrock, It takes only about 2 seconds to penetrate through the water and deep into the underlying limestone and granite. The entire asteroid is compressed, its front flattening against the resistance of the rock, its rear still moving at full speed. This compression generates unimaginable pressures, hundreds of gigapascals, pressures found normally only deep inside the Earth's mantle. At these pressures, the bonds between atoms break down. The rock of the asteroid and the rock of the Earth's crust cease to be rock in any conventional sense. They become a plasma, a state of matter where electrons are stripped from their atoms. This plasma is hotter than the surface of the sun, bright beyond description. If anyone could observe it, which of course no one can, they would be vaporized instantly by the radiation. The expanding plasma generates a shock wave, a pressure front moving outward at hypersonic speed. This shock wave travels through the rock of the Earth's crust faster than sound travels through air. It's not so much a wave as a moving zone of complete destruction, where every molecular bond is broken, where rock is simultaneously compressed, heated, and shattered. The shock wave reaches the surface in less than a second, and when it does, everything in contact with the ground is subjected to accelerations thousands of times stronger than gravity. Meanwhile, the asteroid continues its penetration. Within 3 seconds, it has excavated a crater more than 30 kilometers deep. The energy release is sustained, continuous. As each layer of asteroid and bedrock makes contact, the energy of motion converts to heat. The crater grows downward and outward simultaneously. Rock that's compressed by the shockwave rebounds violently, adding to the excavation. Material is ejected upward at velocities exceeding escape velocity. Some of this material, the fastest moving pieces, will actually leave Earth entirely, entering orbit or even escaping to interplanetary space. Most of the ejected material, though, follows ballistic trajectories. Some of it reaches the upper atmosphere, heating to incandescence as it re-enters. This material will begin to fall back to Earth within minutes, but travelling so fast that it will heat the atmosphere along the entire trajectory. Think of it as millions of meteors, all entering the atmosphere simultaneously, distributed around the globe. The sky, everywhere on Earth, will begin to glow. The crater continues to grow. Rock that was solid and stable is now flowing like water. The bottom of the crater punches through the crust into the upper mantle. The rebound from this compression creates a central peak, a mountain of molten rock pushing upward from the centre of the crater. This peak rises higher than Mount Everest, though it will collapse again within minutes. The violence is difficult to comprehend. This is planetary-scale destruction. The surface of the Earth being reshaped by forces that dwarf anything humans have ever witnessed. All of this happens in the first second, maybe the first few seconds. The asteroid itself has been completely vaporized by now, converted to a rapidly expanding ball of superheated gas and plasma. It no longer exists as a discrete object. It's become part of the Earth, its atoms mixing with the vaporized crust, soon to be distributed around the globe as the dust and vapor that will darken the skies. The energy released in these first seconds is beyond calculation in familiar terms. Every year, human civilization uses about 600 exajoules of energy. The Chicxulub impact released roughly 400 million exajoules in the first second alone. More energy than humanity will use in thousands of years, released in the time it takes to blink. And this was just the beginning. The impact had triggered a cascade of consequences that would unfold over hours, days, months, and years. Let's follow those consequences, starting with the most immediate and moving outward in both space and time. The sky itself was about to catch fire. Within minutes of the impact, the material ejected from the crater began to fall back to Earth. This wasn't ordinary debris. These were particles and fragments travelling at kilometres per second, some still molten, all superheated. As they re-entered the atmosphere, friction heated them further. They became incandescent, glowing white-hot. And there were billions of them, distributed along trajectories that would take them around the globe. The first effect was thermal radiation. The The re-entering ejector heated the air around it, and that hot air radiated infrared energy downward. Within 15 to 30 minutes of the impact, observers anywhere on Earth would have noticed the sky beginning to glow. Not just in the direction of the impact, but overhead, everywhere. The entire sky was becoming an oven. Computer models suggest the thermal pulse was intense enough to ignite plant material on the ground. Forests began to burn spontaneously, not from falling debris but from radiation alone. Imagine standing in a forest as the sky above turns orange, then red, then incandescently bright. The heat becomes unbearable. Leaves begin to smoke, then burst into flame. Within minutes, the entire forest is ablaze, and there's nowhere to run because every direction is the same. The whole world is burning. The fires were global in extent. Fossil evidence shows layers of soot in the KPG boundary clay, soot that represents the combustion of an enormous proportion of Earth's biomass. Estimates suggest as much as 70% of the world's forests burned in the hours and days following the impact. The smoke from these fires would have added to the already catastrophic darkening of the atmosphere, turning day into a twilight that lasted for months. For animals caught in the open, there was no escape from the thermal pulse. Large animals, unable to burrow or find deep shelter, would have been particularly vulnerable. The smaller dinosaurs, the ones that might have otherwise survived the initial shockwave and debris, would have been killed by heat and fire. Even animals that sought shelter in caves or underground would have faced rising temperatures that made those refugees oven-like death traps. The pterosaurs ruling the skies faced a particular horror. The air itself became hostile. The heat from re-entering debris would have created violent updrafts and turbulence. Pterosaurs, with their delicate wing membranes and hollow bones, would have been unable to maintain flight. Many probably fell from the sky, their bodies consumed by the fires raging below. The great Quetzalcoatlus, the largest flying animal ever to exist, likely died in the hours after the impact, its body too large to find adequate shelter, its wings unable to navigate the superheated, turbulent air. In the oceans, the surface waters began to warm. The thermal pulse affected the water less than the land. Of water being a better heat sink, but even a few degrees of warming stressed the marine ecosystems. Fish near the surface faced rising temperatures. The combination of heat and the massive amount of debris falling into the oceans created a toxic environment. Many fish would have died in these first hours, floating to the surface in vast numbers. Too many for even the scavenging species to consume. The fires produced more than just heat and light. They produced carbon monoxide and carbon dioxide in vast quantities, along with a complex mixture of other gases and particulates. The atmosphere's composition began to change within hours. The oxygen content dropped as combustion consumed it. The carbon dioxide content spiked. The air became thick with smoke, with ash, with particulates so fine they could penetrate lungs and damage tissue. Breathing became difficult for any animal that had survived the initial thermal pulse, and still the debris continued to fall. Larger fragments, some the size of boulders, began to impact across North America. These created secondary craters, smaller impacts that added to the destruction. Trees were flattened, lakes were vaporized. The landscape was being reshaped by a bombardment that would continue for hours. By the time the re-entering debris had finished falling, perhaps 12 hours after the initial impact, the world had fundamentally changed. The fires had consumed the majority of Earth's forests. The air was thick with smoke and ash. The thermal pulse had killed anything that couldn't find deep shelter. It was an apocalypse in the truest sense, a revelation of the fragility of life on a planet that orbits through space, vulnerable to the wandering rocks that fill the solar system. But the worst was yet to come. The fires, terrible as they were only the opening act. The real killing mechanism, the thing that would doom even species that survived the impact and fires, was just beginning. The sky was about to go dark, and it would stay dark for a very long time. The impact ejected an estimated 500 cubic kilometers of pulverized rock into the atmosphere, along with vast quantities of soot from the global fires. To understand what 500 cubic kilometres means, consider that Lake Superior contains about 12,000 cubic kilometres of water. The impact threw roughly 4% of Lake Superior's volume in rock dust into the air, but rock is much denser than water. The actual mass of material suspended in the atmosphere was staggering. This material didn't settle quickly. The finest particles, microscopic in size, remained aloft for months, perhaps years. They distributed themselves evenly around the globe, carried by atmospheric circulation, mixing through the troposphere and stratosphere, and they blocked the sun. Not completely, not into absolute darkness, but enough to reduce sunlight to perhaps 1% of normal levels. It would have been like a deep twilight, even at noon on a clear day. Photosynthesis requires light. Plants had evolved for hundreds of millions of years in a world where sunlight was reliable, where the seasons might change but the sun always rose. Suddenly, within days of the impact, they faced conditions where the light reaching the surface was insufficient for most species to photosynthesize effectively. Without photosynthesis, plants couldn't produce energy. They began to die. The collapse of plant life triggered a cascade through the ecosystems. Herbivores, deprived of food, began to starve. The larger the animal, the more food it required, and the faster it would exhaust whatever vegetation remained. The great sauropods, if any survived the fires, would have died within weeks. The ceratopsians and hadrosaurs followed. Even small herbivores faced an impossible situation. The plants they depended on were dying or dead, and what little remained was quickly consumed by desperate competitors. As the herbivores died, the carnivores faced their own crisis. Initially, there was abundant carrion, bodies everywhere. Scavengers would have thrived for a brief time, but dead bodies don't last forever. They decay, or they're consumed. Within months, the carnivores had exhausted their food supply. A Tyrannosaurus requires enormous amounts of meat to survive. With no living herbivores and the carrion consumed, even the apex predators began to starve. In the oceans, the darkness had equally devastating effects. Phytoplankton, the microscopic photosynthetic organisms that form the base of the marine food web, began to die en masse. These organisms normally produce about half of Earth's oxygen and support virtually all marine life. Their die-off triggered a collapse of the ocean ecosystems. The animals that fed on plankton starved. The animals that fed on those animals starved in turn. The extinction spread through the food web like a wave. The ammonites, so diverse and successful for hundreds of millions of years, proved particularly vulnerable. They had complex life cycles that required specific environmental conditions. The disruption of ocean chemistry, the collapse of the food web, the temperature changes all combined to doom them. Every species of ammonite went extinct. After surviving the end-Permian extinction, the end-Triassic extinction, countless smaller crises, they finally met a catastrophe they couldn't survive. The marine reptiles faced similar fates. Mosasaurs, plesiosaurs, all the giant marine predators of the Cretaceous seas depended ultimately on the health of the overall marine ecosystem. As that ecosystem collapsed, they had nothing to eat. Even species that could have survived on carrion for months eventually faced starvation. The oceans, which had been teeming with large reptiles, fell silent. The darkness lasted for months. Some models suggest up to 2 years before light levels returned to something approaching normal. During this time, temperatures dropped significantly. Without sunlight warming the surface, the Earth cooled. This was especially pronounced over the continents. Temperatures may have dropped below freezing across much of the planet. Species that had evolved in the warm, stable climate of the late Cretaceous suddenly faced cold they had no adaptations to handle. The combination of darkness, cold, and food shortage was devastating. It didn't matter how well adapted a species was, how successful it had been, how many millions of years it had survived. If it couldn't find food in the dark, if it couldn't tolerate the cold, if it required the complex ecosystems that were collapsing, it was doomed. Size became a liability rather than an advantage. Large animals required more food and generated more heat loss in the cold. Small animals could survive on less, could find shelter more easily. Gradually, over months and years, the dust began to settle. Light returned to the surface, dim at first, then brighter. The smoke from the fires dispersed. The temperatures began to rise again, but the world the light revealed was transformed beyond recognition. The forests were gone, reduced to ash and charcoal. The dinosaurs were gone, their bones scattered across landscapes now silent and empty. The great marine reptiles were gone, the oceans quieter than they had been in 100 million years. What remained was a planet in shock, ecosystems shattered, the survivors faced with a world utterly different from the one their ancestors had known just months before. But life, as it always does, began the slow process of recovery. Some creatures had made it through, hidden in burrows protected by water, sustained by scavenging or by seeds and detritus. These survivors would inherit the Earth. Let's meet them now, the species that endured when so many others fell. In the months following the impact, the planet was largely silent. The cacophony of the Cretaceous, the calls of hadrosaurs, the roars of tyrannosaurs, the cries of pterosaurs, all had faded into permanent quiet. But not everywhere was silent. In some places life persisted, diminished but determined, carrying on in ways that would eventually lead to recovery. Small mammals, burrowing species that had spent most of their lives underground anyway, found the post-impact world more navigable than most. The darkness didn't affect them as much. They were already adapted to life with limited light. Their burrows provided insulation against the cold. Most importantly, they were generalists, capable of eating a wide variety of foods. Seeds, insects, carrion, plant roots, anything organic was potential food. This flexibility saved them. Among these survivors were the ancestors of modern placental mammals. At the time of the impact, they were small, possibly no larger than rats or shrews. They occupied ecological niches that the dominant dinosaurs ignored, active mostly at night, reproducing quickly, adapting rapidly to changing conditions. The catastrophe that killed the dinosaurs opened the world to them in ways that would have been impossible otherwise. Birds, descendants of earlier dinosaurs, also survived in significant numbers. Not all bird species made it through. Larger birds, particularly those that lived in forests or required specific foods, likely went extinct. But smaller birds, those that could eat seeds or insects, those that could adapt to the changed landscape, survived. Water birds, species that lived along coastlines or on rivers and lakes, proved particularly resilient. They could feed on aquatic invertebrates, on fish if they could catch them, on whatever the water provided. In the oceans, some fish survived in deeper waters where the temperature remained more stable and where they could feed on the rain of organic matter falling from above. The sharks and rays, already ancient lineages by the time of the impact, persisted. Sharks had survived previous mass extinctions, their adaptable body plans and diverse diets giving them an edge when more specialized species failed. They would continue into the New World, largely unchanged. Crocodilians survived almost entirely unscathed. Alligators and crocodiles from the late Cretaceous would have been recognizable to a modern observer. They lived in freshwater environments, feeding on fish, scavenging from carcasses, capable of surviving long periods without food. When the impact came, they simply endured. The darkness meant little to them. The cold could be weathered by entering a state of dormancy. When conditions improved, they emerged, resuming their ancient lifestyle as if nothing had happened. Turtles also survived, protected by their shells, capable of retreating into water or mud to wait out the worst conditions. Lizards and snakes, small and capable of hiding in crevices, feeding on insects and small prey, made it through. Amphibians, with their complex life cycles and ability to survive in both water and land, persisted. The smaller and more adaptable a species was, the better its chances. Plant life began to recover through seeds and spores. Many plants produce seeds that can remain dormant for years, even decades, waiting for favourable conditions. After the impact, these seeds lay in the ash and charcoal waiting. When the light returned, they began to germinate. Ferns were among the first to return, spreading rapidly across the devastated landscapes. The fossil record shows a fern spike immediately after the KPG boundary, a layer rich in fern spores, suggesting these hardy plants were among the first to recolonize the barren ground. Flowering plants, which had been increasing in diversity throughout the Cretaceous, recovered in many lineages. Trees took longer to return, decades or centuries, but they did return. The forests that eventually grew were different from those before the impact, composed of different species, organised into different structures, but forests nonetheless. Life's capacity for recovery, its fundamental resilience, began to assert itself. In the oceans, small fish and invertebrates began to repopulate the waters. Plankton returned, first the hardy species, then others. The food web began to rebuild from the bottom up. It was a slow process, taking thousands of years for anything approaching the diversity and abundance of the Cretaceous seas to return, but it happened. Evolution filled the empty niches, species adapted and diversified. Life flowed back into the spaces left empty by extinction. The key to survival seems to have been flexibility and small size. Animals that could eat a variety of foods, that could tolerate a range of environmental conditions, that didn't require large amounts of energy, these were the ones that made it through. Specialists, those perfectly adapted to specific conditions or food sources, couldn't adapt quickly enough when those conditions changed catastrophically. They vanished, leaving only fossils to mark their existence. And so, the Earth began to heal, slowly, gradually, with setbacks and false starts, but persistently. The crater at Chicxulub filled with water, then with sediment. The fire's ash became part of the soil. The bones of the dinosaurs weathered and eroded, most disappearing entirely, a few becoming fossils that would wait millions of years to be discovered. The survivors spread out into a world suddenly full of opportunities, niches left empty by the extinction, roles waiting to be filled. What survived and what didn't follows patterns we can now recognise, patterns that tell us much about the nature of extinction and survival. The pattern of survival across the KPG boundary reveals some fundamental truths about mass extinctions. This wasn't a selective catastrophe that targeted particular lineages or spared others based on some characteristic we might find meaningful. It was opportunistic, chaotic, following rules that make sense only in retrospect. Among the dinosaurs, only birds survived, but not all birds. The large flightless birds went extinct. The tree-dwelling birds that depended on forests largely perished. What survived were mostly ground-dwelling birds, species that could nest in burrows or on the ground, that ate seeds or insects, that were small enough to survive on limited resources. The connection isn't to the birds being, quote, "3" in any general sense, but to them happening to possess characteristics that matched the post-impact conditions. The pterosaurs went entirely extinct, every species. This is particularly interesting because pterosaurs had been enormously successful for over 150 million years. They had colonized every aerial niche, from tiny insectivores to giants with wingspans approaching 10 meters. But they couldn't survive the impact. Why? They required warm temperatures to maintain their metabolism. They needed reliable food sources. Many were too large to hide from the thermal pulse. Their bones were hollow and fragile, their wing membranes delicate. The environmental chaos was simply too much. On land, the pattern was stark. Nothing larger than about 25 kilograms survived if it wasn't capable of burrowing, swimming, or flying. This size cutoff isn't precise, and there were exceptions, but it holds broadly. Large animals require more food, more space, more stable conditions. They couldn't weather the months of darkness and cold. Even if they survived the initial impact and fires, they starved in the aftermath. In the oceans, the extinctions followed different patterns. The ammonites, as we discussed, went completely extinct despite being extraordinarily diverse. The marine reptiles vanished entirely, but many fish survived. Most shark lineages made it through. What determined survival in the oceans seems to have been depth and dietary flexibility. Species that lived in deeper water, or that could eat a variety of foods, had better chances. Surface-dwelling specialists were doomed. Coral reefs collapsed almost entirely. Modern scleractinian corals survived. But they took millions of years to recover their diversity and abundance. The KPG boundary marks one of the great reef gaps in geological history, a time when these ecosystems simply didn't exist in any substantial form. The corals that eventually rebuilt the reefs were different species, adapted to the new ocean chemistry and temperature regimes. Freshwater environments proved to be refuges. Freshwater fish, turtles, crocodilians and amphibians all survived at higher rates than their saltwater or terrestrial counterparts. Why? Freshwater ecosystems are somewhat isolated from the wider catastrophe. They have their own food webs based on local detritus and organic matter. The darkness affected them certainly, but they had buffers that purely terrestrial or marine ecosystems lacked. Plants show an interesting pattern. Flowering plants suffered significant extinctions but recovered their diversity relatively quickly. Conifers took a harder hit in some regions but survived in others. Ferns, as mentioned, thrived immediately after the impact. The plant extinctions seem related to fire tolerance and seed survival more than any other factor. Species with fire-resistant seeds or that could regenerate from underground structures had advantages. What's striking, when we look at the overall pattern, is that survival wasn't about being advanced or primitive, simple or complex. The crocodilians, with their ancient body plan virtually unchanged for 200 million years, survived. The ammonites, with their complex shells and sophisticated life cycles, went extinct. The mammals, small and generalized, survived. The dinosaurs, dominant and diverse, perished. Success in one era provided no guarantee for the next. This randomness is perhaps the most unsettling aspect of mass extinctions. We like to think that survival is about fitness, about being well adapted, about having the right characteristics. And in normal times, that's true. But during catastrophic events, survival often comes down to luck. Being in the right place, being the right size, eating the right foods, not because those things are inherently superior, but because they happen to match the radically altered conditions. The animals that went extinct weren't inferior. The dinosaurs weren't evolutionary dead ends. They were magnificently adapted to the world they lived in, a world that had existed for millions of years and showed every sign of continuing indefinitely. They were victims of circumstance, of being on a planet when a rock from space happened to fall, of size and metabolic requirements that served them well for millions of years, but became liabilities in the months after the impact. And the survivors weren't necessarily superior. They were lucky. Lucky to be small, lucky to eat the right foods, lucky to live in the right places. The mammals that inherited the Earth weren't waiting in the wings, preparing to overthrow the dinosaurs. They were marginal, nocturnal creatures that happened to possess characteristics that allowed them to endure when larger, more dominant animals could not. Understanding this randomness, this contingency, changes how we view life's history. The world we know, with its mammals and birds, its particular distribution of species and ecosystems, wasn't inevitable. It resulted from a specific catastrophe that happened to occur 66 million years ago. If the asteroid had missed Earth, if it had struck a few million years earlier or later, if it had been smaller or larger, the present would be different in ways we can barely imagine. Our existence isn't the culmination of progress, but the result of fortunate accidents compounded over vast time. That thought deserves some contemplation. The dinosaurs left behind their bones, and those bones, transformed to stone over millions of years, are our windows into their final days. Paleontology is detective work, piecing together stories from fragments, reading histories written in stone. The KPG boundary deposits around the world have yielded remarkable fossils, each one a data point in understanding the extinction. In the Hell Creek Formation of Montana, paleontologists have collected thousands of fossils from the latest Cretaceous. The formation represents about 2 million years of deposition, ending right at the KPG boundary. By carefully mapping where each fossil was found and in which layer, researchers can track changes in dinosaur populations leading up to the extinction. What they've found is that dinosaur diversity was high right up to the boundary. There's no evidence of gradual decline, no hint that the dinosaurs were already struggling before the impact. The fossils show healthy populations. There are juveniles, indicating successful reproduction. There are old individuals suggesting low predation pressure and adequate food. The bone chemistry shows they were well nourished. These weren't populations in decline, they were thriving populations that ended abruptly. One of the most poignant fossils ever discovered is a Triceratops bone found just centimetres below the KPG boundary in Montana. The bone is complete, well preserved, showing no signs of scavenging or weathering before burial. This animal was alive just before the impact. It probably died in the catastrophe itself or in the immediate aftermath. It lived its entire life in a world where dinosaurs were dominant, and it died at the exact moment that dominance ended. The precision is haunting. In marine deposits, the story is equally clear. Ammonite fossils are abundant in rocks just below the boundary. Beautiful spiraled shells, some small as a fingernail. Others large as truck tires show an extraordinary diversity. Every major group of ammonites is represented, and then, at the boundary, nothing. Not a gradual decline, not a slow replacement by other species, but complete absence. The last ammonite lived its life, died, sank to the seafloor, was buried by sediment. Above that layer, no ammonites ever existed again. Fossil pollen tells its own story. Researchers can extract pollen from sediments and identify it to species or family level. Below the KPG boundary, pollen assemblages show diverse forests dominated by flowering plants, conifers, and cycads. Immediately above the boundary, there's the fern spike we mentioned earlier, massive quantities of fern spores suggesting these hardy plants were the first to recolonize devastated landscapes. Then, gradually, other plant species return but in different proportions, forming new communities that never quite match the pre-impact forests. The fossils also preserve traces of the impact itself. Shocked quartz grains show the characteristic microscopic fracture patterns that only form under extreme pressure. Tektites, small glass beads formed when rock is melted and flung into the air, have been found in boundary deposits around the world. Some contain bubbles of ancient atmosphere, trapped at the moment of their formation, providing clues about atmospheric conditions. Perhaps most remarkably, there are fossils that seem to capture the impact's immediate aftermath. The Tanis site in North Dakota, discovered by paleontologist Robert De Palma, contains fossils of animals that appear to have died within hours of the impact. Fish with impact spherules in their gills, pterosaur bones mixed with impact debris, plant material showing signs of having been burned. This isn't a typical fossil deposit accumulated over thousands of years. This is a snapshot, a moment frozen in time. The Tanis fish died while the impact debris was still falling from the sky. They breathed in the spherules, tiny glass beads formed in the impact fireball, and ejected on ballistic trajectories that brought them down in North Dakota within an hour of the impact. The fish were going about their normal lives in a river or lake, unaware that 2,000 miles away their world had just ended. The spherules fell like rain, and the fish inhaled them and died, and were quickly buried by sediment stirred up by the impact's seismic waves. Every fossil tells a story, but these KPG boundary fossils tell perhaps the most dramatic story in paleontology. They document the end of an era, the last moments of species that had ruled the Earth for over 160 million years. They show us that extinction can be sudden, complete, and unrelated to any failure or inadequacy of the species that perish. They remind us that our planet has a history far longer and more dramatic than our brief human experience suggests, and they point us toward a specific moment, a specific event, a day when everything changed. Thanks to sites like Tanis, we can reconstruct that day with increasing precision, understanding not just that the dinosaurs went extinct, but how, and how quickly, and what the final hours might have been like. The fossils are our connection to deep time, our way of reaching back across 66 million years to touch, however briefly, a world that no longer exists. The Tanis site, officially part of the Hell Creek Formation, sits in North Dakota's Badlands, a landscape of eroded hills and exposed sedimentary layers. Robert de Palma began excavating here in 2013, and what he found was unprecedented. The site contains a mass death assemblage from the KPG boundary, but unlike other boundary sites, this one appears to preserve the actual day of the impact, the hours immediately following the asteroid's collision. The evidence is in the details. The fish fossils, primarily sturgeon and paddlefish, show no signs of the usual decomposition and scavenging you'd expect if they had died and lain exposed for days before burial. Instead, they appear to have been buried rapidly while still fresh. Their bodies are articulated, bones still in proper arrangement, suggesting they were covered quickly by sediment. But what killed them? The answer lies in the spherules found in their gills. These tiny glass beads, formed when molten rock is ejected from the impact site and cools while airborne, have a very specific composition that matches the Chicxulub crater. Dating places them at exactly the KPG boundary. The fish have these spherules in their gill structures, which means they were breathing when the spherules fell. They inhaled the impact debris and died, likely from the combination of physical damage to their gills and the shock of the impact's effects. The spherules would have been travelling at high speed when they hit the water, having followed ballistic trajectories from the impact site. They would have fallen like a rain of tiny meteors, each one glowing hot. The water would have hissed and steamed where they landed. For the fish, it would have been a sudden, inexplicable assault. The water around them filling with strange burning particles. But the spherules weren't the only factor. Tanis also shows evidence of massive seiche waves, standing waves in bodies of water caused by ground shaking. The impact generated seismic waves equivalent to a magnitude 10 or 11 earthquake, far larger than any earthquake in human history. These waves travelled through the Earth's crust at several kilometres per second. They reached North Dakota, about 2,000 miles from the impact site, within minutes. The seismic waves shook the ground violently. Any standing water would have sloshed back and forth in massive surges, like water in a bathtub that's been struck. These seiche waves could have been metres high, possibly tens of metres. They would have surged back and forth for hours as the ground continued to shake. The sediments at Tanis show layering consistent with multiple surges of water, depositing and redistributing material. The combination killed and buried the fish rapidly. The seismic waves stirred up sediment. The water became thick with suspended mud and sand, the spherules fell from the sky, and the fish died in this chaos, their bodies immediately covered by the churning sediment. It was a death trap, but for paleontologists, it's a treasure trove, a window into the impact's immediate effects. Among the fish fossils, De Palma found other remarkable specimens. There's a pterosaur embryo inside an egg, the developing creature visible through the shell. There are fragments of Triceratops skin, likely washed in by the seiche waves. There are plants showing evidence of having been burned. There are insects trapped in amber. Each fossil adds detail to the picture, helping researchers understand the sequence of events. The site also contains high concentrations of iridium in the exact layer with the dead fish. Confirming the timing, there are shocked minerals, tektites, all the signatures of impact. But unlike most boundary sites, which represent a gradual accumulation of material over perhaps thousands of years, Tanis seems to represent a single day, perhaps just a few hours. Think about what that means. We can examine fossils from the actual day the dinosaurs died. We can see the impact debris falling. We can trace the seismic waves' effects. We can understand the immediate chaos. It's as close as we're likely to get to witnessing the event itself, and it's only possible because of a quirk of preservation, a set of conditions that buried these organisms so quickly that their final moments were frozen in stone. The Tanis site has been controversial in paleontology. Some researchers question the interpretation, suggesting the deposit might represent a longer time period or different events. Science works through debate and reanalysis, and the Tanis findings will continue to be studied and tested. But even if some details are revised, the site undeniably preserves remarkable evidence of the impact's immediate aftermath. What's particularly moving about Tanis is how it humanizes, or perhaps naturalizes, the extinction. These weren't abstract statistics, percentages of species lost. These were individual organisms, living their lives, completely unaware of what was happening 2,000 miles away. They experienced the catastrophe directly, the seismic waves, the falling spherules, the churning water. Their deaths were part of the largest mass mortality event in Earth's history, but they were also individual deaths, each creature experiencing its own end. The fish at Tanis connect us emotionally to the extinction in a way that statistical analyses cannot. They died in confusion and pain, not understanding what was happening, incapable of understanding, and their story is preserved, waiting 66 million years for someone to find it and piece it together. It's a profound gift to science and to our understanding of Earth's history. Behind every scientific discovery are people, individuals driven by curiosity and sustained by persistence. The story of how we came to understand the dinosaur extinction is also a story of scientists working across decades, building on each other's findings, sometimes competing, sometimes collaborating, always pushing toward better understanding. Luis and Walter Alvarez, the father-son team who discovered the Iridium anomaly, came from different scientific traditions. Luis was a physicist who had worked on radar technology during World War II and later contributed to the Manhattan Project. He was skilled at applying physics to solve problems in other fields. Walter was a geologist, trained in reading rocks and understanding Earth's history. Their collaboration brought together expertise from both disciplines. When they found the elevated iridium levels in the boundary clay, they didn't immediately jump to an asteroid impact. They considered other explanations. Could the iridium have come from volcanic eruptions? Could it represent a longer period of accumulation? They tested these alternatives systematically, measuring iridium concentrations in samples from around the world, always finding the same spike at the same geological moment. Only after exhausting other possibilities did they propose the impact hypothesis. The scientific community's initial skepticism was healthy, even necessary. Extraordinary claims require extraordinary evidence, and the Alvarezes were claiming that an event from science fiction, an asteroid striking Earth, had caused the most famous extinction in history. Many paleontologists had spent careers developing alternative explanations for the dinosaur extinction. They weren't inclined to abandon those explanations based on a single element's concentration, but the evidence accumulated. Geophysicists Jan Smit and others found the iridium layer in dozens of locations. The shocked quartz and tektites pointed unmistakably to impact. The global distribution of the boundary layer showed this was a worldwide event, not something regional. Each piece of evidence narrowed the possibilities until impact became not just plausible but probable. Finding the crater required different skills. Alan Hildebrand, working in the late 1980s, was convinced the crater existed and should be enormous. He searched through geological surveys, petroleum exploration data, gravity anomaly maps, anything that might hint at a massive buried structure. When he learned about the Chicxulub circular feature in the oil company records, he recognized it might be what he was looking for. Confirming it was Chicxulub required collaboration with Mexican scientists, particularly Antonio Camargo and Glenn Penfield, who had worked on the original petroleum surveys. It required new drilling, new dating, chemical analysis of the rocks. The work took years. But gradually the case became irrefutable. This was the impact crater. This was ground zero. Throughout the 1990s and 2000s, hundreds of scientists contributed to understanding the extinction mechanism. Climate modelers like Brian Toon and Kevin Pope simulated the impact's atmospheric effects. Paleontologists like David Fastovsky and Peter Sheehan analysed fossil distributions. Geochemists studied the boundary layer's composition. Each discipline added pieces to the puzzle. Robert De Palma's discovery of Tanis represents a newer generation of researchers bringing fresh perspectives. His meticulous excavation techniques and careful analysis of the site have provided unprecedented detail about the impact's immediate aftermath. His work demonstrates how paleontology continues to advance, how new discoveries can still surprise us even in well-studied formations. What strikes me about these scientists is their patience. Luis Alvarez didn't live to see the crater definitively identified. He died in 1988, just as the Chicxulub structure was being confirmed. Walter Alvarez has spent decades since the original discovery defending and refining the impact hypothesis. Hildebrand worked for years before finding Chicxulub. De Palma has spent over a decade excavating Tanis. Science moves slowly sometimes, requiring sustained effort over careers or even lifetimes. The story also shows how science self-corrects. The initial theories about dinosaur extinction, gradual decline due to climate change or competition with mammals, weren't stupid. They were based on the evidence available at the time. When new evidence emerged, the theories changed. Some scientists resisted, certainly, but the community as a whole moved toward the better explanation. This is how science is supposed to work. There's also something beautiful about the interdisciplinary nature of the discovery. Physics, geology, paleontology, chemistry, climate science all contributed. No single discipline could have solved the mystery alone. The impact hypothesis required bringing together knowledge from across the sciences, specialists working on pieces of a problem too large for any one person to comprehend fully, and the work continues. New drilling programs at Chicxulub reveal more about the impact's mechanics. New fossil sites provide more data about the extinction pattern. Improved climate models refine our understanding of the environmental effects. Each year brings publications adding to our knowledge, answering old questions and raising new ones. The scientists who solved this mystery gave us something profound, an understanding of one of Earth's greatest catastrophes, a window into deep time. Proof that our planet has a dynamic history where sudden change is possible. They showed us that we live on a world that orbits through space, vulnerable to cosmic accidents, and they did it through careful work, collaboration, and a willingness to follow evidence wherever it led. Their legacy is the story we're telling tonight, pieced together from rocks and calculations and inspired interpretation. 66 million years separates us from the last day of the dinosaurs. Let's try once more to grasp this span, to feel its weight, because without understanding the time involved, we can't fully appreciate the story. Deep time is difficult for human minds to comprehend. Our lives are short, our recorded history brief. We struggle to imagine even thousands of years, let alone millions. Consider that if each year since the impact were a single step forward, you'd need to walk around the Earth's equator 1.5 times to cover the distance. If each year were 1 second, 66 million years would equal roughly 2 years of continuous time passing. These analogies help somewhat, but they still fall short of conveying the sheer vastness involved. What has happened in those 66 million years? Continents have moved thousands of kilometers. India collided with Asia, raising the Himalayas. The Atlantic Ocean widened by thousands of miles. Entire mountain ranges rose and eroded away. Vast inland seas appeared and disappeared. The climate swung from ice ages to tropical warmth and back again, many times over. And through all of this, life evolved, filling the niches left empty by extinction. The mammals, small and generalized at the time of the impact, diversified explosively. Within 10 million years, there were mammals of all sizes occupying all major terrestrial niches. There were large herbivores, small insectivores, predators, scavengers, specialized forms for every environment. They evolved into whales and returned to the seas. They evolved wings and took to the air as bats. They developed complex social behaviors, large brains, remarkable adaptations. Birds also diversified, evolving from their dinosaurian ancestors into the incredible variety we see today. From tiny hummingbirds to massive ostriches, from penguins swimming in Antarctic waters to albatrosses soaring over oceans, the birds adapted and spread. They're the living dinosaurs, the only lineage that survived the impact, and they've made the most of their inheritance. The flowering plants, which had been relatively new at the time of the impact, came to dominate terrestrial ecosystems. They co-evolved with insects, developing ever more intricate relationships. The grasses, a particular family of flowering plants, appeared about 55 million years ago and transformed vast regions into prairies and savannas. These grasslands supported new forms of mammalian herbivores, which in turn supported new predators. The ecosystems became as complex and diverse as anything in the Cretaceous, though utterly different in composition, and eventually, after 65.5 million years, our own lineage appeared. The primates evolved from small arboreal mammals, gradually developing larger brains and more complex social behaviors. Our ancestors descended from the trees, began walking upright, started using tools. Modern humans, Homo sapiens, appeared perhaps 300,000 years ago. All of recorded human history, everything we consider civilization, spans maybe 5,000 years. We're the newest thing on this planet, the most recent experiment in life's long story. From the perspective of deep time, we're barely here. If the 66 million years since the impact were compressed into a 24-hour day, humans would appear in the last second before midnight. Our entire species' existence is a blink. Recorded history is immeasurably brief, too short to register on geological timescales. Yet in that brief moment, we've developed the capacity to understand deep time itself, to read the rocks, and piece together stories spanning millions of years. This ability to understand our own history, to see ourselves as part of a continuum stretching back billions of years, is perhaps uniquely human. No other species, as far as we know, contemplates deep time. No other species excavates fossils to understand ancient extinctions. We're the only ones who can look at a dinosaur bone and comprehend that it represents a creature that died millions of years before our ancestors existed. What does this perspective give us? Humility, certainly. We're not the culmination of the life's journey, but simply the current occupants of a planet with a long and ongoing story. Our existence wasn't inevitable. If the asteroid had missed, if some other catastrophe had befallen the dinosaurs earlier or later, if the mammals hadn't survived the impact, we wouldn't be here. Our lineage exists because of a cosmic accident 66 million years ago. But there's also something empowering in this perspective. We can understand deep time. We can appreciate the vast sweep of life's history. We can recognize patterns, see connections, understand how Earth's systems work over millions of years. This knowledge makes us responsible, stewards of a planet whose history we've uncovered and whose future we influence. 66 million years is long enough for entire worlds to rise and fall, for life to reinvent itself completely, for continents to rearrange and climates to transform. Yet it's also short enough that evidence remains, that we can still read the story in rocks and fossils. The KPG boundary sits there in geological formations worldwide, a thin dark line marking the moment when everything changed. We can visit it, touch it, analyze it. Deep time isn't abstract. It's real, recorded in stone, waiting for anyone willing to look. And when we do look, when we really try to comprehend the 66 million years separating us from the dinosaurs' last day, we realize that our perspective shifts. Problems that seem overwhelming on human timescales become smaller. Projects that seem long become brief. Our individual lives, our empires and civilizations, our triumphs and catastrophes all take on a different proportion when viewed against deep time's vastness. This isn't to diminish human experience, but to contextualize it, to see ourselves as part of something far larger and longer running than we sometimes remember. The KPG extinction wasn't unique in Earth's history. It was dramatic, certainly, and it has captured public imagination because it killed the dinosaurs, but it wasn't even the largest mass extinction. Understanding the pattern of mass extinctions helps us see the KPG event in context, as one episode in a longer story of life's resilience and vulnerability. Paleontologists recognize 5 major mass extinctions in the past 540 million years, the period since complex hard-bodied organisms became common enough to leave abundant fossils. The KPG extinction was the 5th and most recent of these. Before it came 4 other catastrophes, each with its own cause and its own pattern of survival and death. The first major mass extinction occurred at the end of the Ordovician period, about 445 million years ago. This event was probably caused by rapid climate change, a shift from greenhouse conditions to a severe ice age and back again. About 85% of species went extinct, mostly marine organisms since little lived on land at that time. The extinction cleared the way for new groups to evolve and diversify. The second, at the end of the Devonian period about 375 million years ago, took place over several million years. Multiple causes have been proposed, including asteroid impacts, volcanic activity, and ocean anoxia, the depletion of oxygen in seawater. About 75% of species died, including many fish and the first amphibians' ancestors. This extinction shaped the evolution of terrestrial vertebrates, our distant ancestors. The third mass extinction, at the end of the Permian period 252 million years ago, was the most severe in Earth's history. About 96% of all marine species and 70% of terrestrial species went extinct. The cause was likely massive volcanic eruptions in Siberia, the Siberian Traps, which released enormous quantities of carbon dioxide and other gases, causing dramatic climate warming and ocean acidification. The extinction was so severe that it took millions of years for ecosystems to fully recover. This event cleared the stage for the dinosaurs, who emerged in the Triassic period that followed. The fourth mass extinction, at the end of the Triassic period about 201 million years ago, killed about 80% of species. Volcanic activity, possibly related to the breakup of the supercontinent Pangaea, has been implicated. This extinction hit marine ecosystems particularly hard. On land, it affected early dinosaurs and other reptiles, but also opened niches that the surviving dinosaurs would exploit, leading to their diversification in the Jurassic period. What patterns emerge from these 5 catastrophes? First, mass extinctions are rare. There have been only 5 in 540 million years, averaging 1 every 100 million years or so. Between these major events, there have been smaller extinction pulses, times when species diversity dropped significantly, but not catastrophically. Extinction is always occurring at some background rate, but mass extinctions represent times when that rate spikes dramatically. Second, the causes vary. The KPG extinction was caused by an asteroid impact. The Permian extinction was likely volcanic. The others had different causes or combinations of causes. There's no single mechanism that triggers all mass extinctions. Earth has multiple ways of becoming hostile to life, and over enough time most of them eventually occur. Third, recovery takes time. After each mass extinction, life rebounds. But not immediately. The fossil record shows that it typically takes millions of years for ecosystems to regain their previous complexity and diversity. The pace of recovery depends on how severe the extinction was and how much of the environment was damaged. After the Permian extinction, recovery took nearly 10 million years. After the KPG extinction, ecosystems were functioning again within a few million years, though they looked very different from before. Fourth, mass extinctions reset evolutionary trajectories. They clear away dominant groups and create opportunities for previously marginal lineages. If the Permian extinction hadn't occurred, dinosaurs might never have risen to dominance. If the KPG extinction hadn't occurred, mammals might still be small nocturnal creatures. Extinctions create possibilities even as they destroy. Fifth, the survivors shape the future. What survives a mass extinction isn't random, but it's not necessarily what we'd predict based on success before the extinction. Small size, dietary flexibility, ability to shelter or hibernate, these characteristics help during catastrophes. But the species that possess these traits aren't necessarily the ones that will dominate afterward. Evolution in the aftermath takes its own path. Looking at this pattern, we can see that Earth's history is punctuated by catastrophe. Long periods of relative stability are interrupted by sudden, dramatic changes that reshape life completely. This pattern suggests that our current world, with its particular mix of species and ecosystems, is temporary. Not on timescales that matter to individual humans or even to human civilization, but on geological timescales. Eventually there will be another mass extinction. The question isn't whether, but when. Currently, some scientists argue we're in the midst of a sixth mass extinction, this one caused by human activity. Habitat destruction, climate change, pollution, and overharvesting are driving species extinct at rates that may rival the major extinctions of the past. Whether this is truly comparable to the KPG or Permian extinctions is debated, but it's clear that humans are having an outsized impact on biodiversity. Understanding the pattern of past mass extinctions informs how we think about our current impact. We know that ecosystems can recover from catastrophic damage, but we also know recovery takes millions of years. Timescales meaningless to human civilization. We know that mass extinctions eliminate the dominant groups and create opportunities for others, but we're currently the dominant group, and our survival through a mass extinction we're causing is far from certain. The KPG extinction sits in this larger context, one of 5 great catastrophes, each unique but each part of a pattern. Life persists, adapts, recovers. But the life that recovers isn't the same as what came before. The dinosaurs ruled for over 160 million years, but when they fell completely. Their world ended, and a new world began. We're living in that new world, descendants of the small mammals that survived when the great reptiles perished. The Earth after the impact was broken, silent, seemingly lifeless. The forests were ash. The dinosaurs were dead. The oceans were depleted. But life had not ended. It had merely been reduced, simplified, pushed to its limits. And from those limits, it began the slow work of recovery. Demonstrating a resilience that defies easy explanation. In the first 1,000 years after the impact, the most successful organisms were the decomposers and scavengers. There was an enormous amount of dead biomass, bodies and burned vegetation covering landscapes. Bacteria and fungi broke down this material, recycling nutrients back into the soil. Scavenging animals, anything that could eat carrion, thrived for a brief time. The immediate post-impact world was, paradoxically, rich in one resource, organic matter from everything that had died. But as the carrion was consumed and the smoke cleared and light returned, different challenges emerged. The survivors needed to eat, to reproduce, to establish populations. The early recovery phase was dominated by opportunistic species, those that could exploit disturbed environments. Think of modern ecosystems after forest fires or volcanic eruptions. The first plants to return are often weeds, species that grow quickly, reproduce rapidly, and aren't picky about conditions. The same pattern likely played out after the KPG extinction. Ferns, as we mentioned, were among the first plants to recolonize the devastated landscapes. Their spores are hardy, capable of surviving long periods of dormancy. They germinate readily in disturbed soil. A fern doesn't need complex ecosystems to get started, just bare ground and sunlight and water. So for a time, perhaps thousands of years, the continents were covered in fern prairies, simple ecosystems where ferns dominated and little else grew. Gradually, other plants returned, flowering plants from surviving seeds, conifers from protected refuges. Slowly, over thousands of years, forests began to regrow. Though they were different from the Cretaceous forests, the species composition had changed. Some plant families that had been dominant before the impact were now reduced or extinct. Others, previously minor, became more important. The new forests were collaborations between survivors, ecosystems built from whatever had made it through. As plants returned, herbivores followed. The mammals, freed from competition with dinosaurs, began to diversify. Within the first million years after the impact, there were already mammals significantly larger than their Cretaceous ancestors. Evolution works quickly when there are empty niches to fill. The mammals spread into ecological roles that dinosaurs had previously occupied, though they did so in their own ways, developing uniquely mammalian solutions to the challenges of herbivory and predation. In the oceans, recovery was slower. The marine food web had collapsed almost completely. It had to rebuild from the bottom up, starting with the return of phytoplankton. These microscopic photosynthesizers are fundamental to ocean life. As they returned, they supported zooplankton, which supported small fish, which supported larger fish and marine mammals. The process took millions of years. The great marine reptiles were gone forever, but sharks and bony fish diversified, eventually filling many of the vacated niches. Birds, those surviving dinosaurs, underwent their own evolutionary radiation. Freed from competition with pterosaurs and with many ecological niches empty, they diversified rapidly. Within 10 million years of the impact, birds had evolved into many of the major lineages we recognize today. Some remained small and arboreal, others became large and flightless, some took to the water. The evolutionary experimentation was exuberant, life testing countless variations on the bird body plan. By 10 million years after the impact, the planet was thriving again. The forests were diverse and complex. The mammals included forms adapted to every terrestrial environment. The birds filled the skies. The oceans teemed with life. If you could visit Earth 10 million years post-impact, you would recognize it as alive, vibrant, full of complex ecosystems. But you would also see that it was completely different from the late Cretaceous. The species were new. The ecological structures were rearranged. The dominant groups were different. This recovery demonstrates something profound about life: its ability to persist and diversify even after catastrophic setbacks. The KPG extinction eliminated 3/4 of all species. It destroyed ecosystems that had existed for millions of years. It killed organisms that had been successful for longer than most lineages survive. And yet, within a geological eye blink, life had recovered its complexity, though not its composition. What drove this recovery? Partly, it's simply what life does. Organisms reproduce, populations grow. Evolution generates variation. Natural selection favours the variations best suited to current conditions. Over enough generations, this process produces diversity and complexity. Give life empty niches and time, and it will fill them. But there's also something more, something harder to quantify. Life seems to have an inherent tendency toward complexity. Left to its own devices, over millions of years, it builds elaborate ecosystems, intricate relationships between species, complex food webs. We don't fully understand why this is. It may be that complex ecosystems are simply more stable, better at resisting perturbations. it may be that the interaction between species drives evolutionary innovation. Whatever the reason, life tends toward richness and diversity. The recovery after the KPG extinction showed this tendency in action. The world could have remained simple, dominated by a few successful generalist species. Instead, it became complex again, diverse, full of specialists and intricate relationships. Evolution took the surviving lineages and elaborated them into the rich tapestry of life that would characterize the Paleogene period. And from that tapestry would eventually emerge our own lineage, the primates, the mammals that would lead to us. The recovery made us possible. The mammalian radiation after the KPG extinction is one of evolution's greatest success stories. From small, generalized ancestors that lived in the shadow of dinosaurs, mammals diversified into virtually every ecological niche on land, and many in the sea and air as well. This radiation happened relatively quickly, in geological terms, and it fundamentally reshaped terrestrial ecosystems. At the time of the impact, mammals were diverse but small. The largest mammal in the late Cretaceous was about the size of a badger. Most were much smaller, mouse-sized or rat-sized creatures. They were primarily nocturnal, avoiding the heat of the day and the attention of dinosaurian predators. They ate insects, seeds, perhaps small vertebrates. They were successful in their way, but marginal, confined to niches the dominant dinosaurs didn't occupy. The impact changed everything for mammals. Suddenly the constraints were removed. Daytime was no longer dangerous. Large size was no longer impossible. New food sources were available. The mammals responded to these new opportunities with explosive diversification. Paleontologists call this kind of rapid evolution an adaptive radiation, and the mammalian radiation after the KPG extinction was one of the most dramatic ever recorded. Within 10 million years there were mammals as large as bears. Within 20 million years there were mammals larger than any dinosaur, massive herbivores and the predators that hunted them. The diversification wasn't just about size, though. Mammals evolved new dietary strategies. There were specialized herbivores with complex teeth for grinding tough plant material. There were carnivores with sharp teeth for tearing flesh. There were omnivores that ate whatever they could find. There were insectivores with tiny sharp teeth for cracking exoskeletons. Mammals also evolved new locomotion strategies. Most early mammals were probably relatively clumsy runners, using a sprawling gait like modern lizards. But after the extinction, some lineages evolved more efficient gaits. The limbs moved under the body rather than to the sides. This allowed for faster running, greater endurance. Some mammals became specialized jumpers, like the ancestors of kangaroos. Others became climbers, developing grasping hands and feet for life in trees. Still others returned to the water, their limbs transforming into flippers, eventually evolving into fully aquatic forms like whales and seals. The primate lineage, our ancestors, emerged during this radiation. The earliest primates appeared perhaps 60 million years ago, just 6 million years after the impact. They were small, arboreal animals with grasping hands and feet, forward-facing eyes that provided depth perception, and relatively large brains. They lived in trees, eating fruits and insects, using their excellent eyesight and coordination to navigate the three-dimensional world of the forest canopy. Why did primates evolve? The flowering plants that had survived and diversified after the extinction produced fruits, nutrient-rich packages designed to entice animals to disperse their seeds. The primates specialized in finding and eating these fruits. This diet favored intelligence, color vision to identify ripe fruit, and memory to recall where fruiting trees were located. Over millions of years, these selective pressures pushed primates toward larger brains and more complex behaviors. From those early primates would eventually evolve monkeys, apes, and ultimately humans. But that took tens of millions of years. In the Paleogene period, the time immediately after the extinction, primates were just one among many mammalian lineages. Not obviously destined for anything special, What's remarkable is how quickly the diversification occurred. Go back to the latest Cretaceous, just before the impact, and you find mammals confined to small body sizes and limited ecological roles. Jump forward 10 million years, and you find mammals of all sizes filling all roles. It's as if evolution had been waiting for the opportunity and, when given it, exploded into action. This rapid radiation illustrates how evolution works. It's not a slow, steady process of incremental change. Sometimes it's fast, punctuated, driven by new opportunities or environmental changes. The dinosaurs' extinction created those opportunities for mammals, and evolution took full advantage. Of course, the mammals didn't just fill the roles dinosaurs had occupied. They did things their own way, bringing mammalian characteristics to bear. They were warm-blooded, maintaining constant body temperature, which allowed them to be active at night or in cold climates. They gave birth to live young and nursed them, providing parental care that ensured higher survival rates. They had more complex brains, capable of learning and flexible behaviour. These advantages, combined with the empty niches left by the dinosaurs' extinction, allowed mammals to dominate the Cenozoic era, the age of mammals that continues to this day. Looking back from our perspective, it's tempting to see the mammalian radiation as inevitable, as if mammals were always destined to replace dinosaurs. But that's not how evolution works. If the asteroid had missed Earth, the dinosaurs would likely still be dominant today. Mammals might still exist, but confined to their Cretaceous niches, small and nocturnal and marginal. Our existence, human existence, depended on the asteroid striking when and where it did. This contingency is worth contemplating. We're here because of a catastrophe. Because 66 million years ago, a piece of rock happened to intersect Earth's orbit at precisely the wrong moment. Our lineage didn't outcompete the dinosaurs. We didn't evolve superior adaptations that allowed us to overthrow them. We simply survived an accident that they didn't, and then our ancestors exploited the opportunities that accident created. There's no grand design here, no inevitable progression toward human intelligence. Just chance, opportunity, and evolution's relentless capacity to fill empty niches with new forms. Let's engage in a thought experiment, a gentle exploration of what might have been. Imagine the asteroid had missed Earth. Imagine it passed by harmlessly. Close enough perhaps that if dinosaurs could understand such things, they might have noticed a bright object in the sky for a night or two, but then it was gone, continuing on its orbit never to return. What would Earth be like today? The dinosaurs would still be here, almost certainly. There's no evidence they were in decline before the impact. No other catastrophe appears on the horizon in the fossil record. They were thriving, diverse, successful. If the impact hadn't occurred, they would have continued into what we call the Cenozoic era. Still dominant, still diverse, still evolving. What would they have evolved into? That's harder to answer. Evolution is responsive to environmental pressures and opportunities. We can't predict exactly what those would have been over the next 66 million years, but we can speculate carefully based on trends we see in the fossil record and our understanding of evolutionary processes. The ceratopsians might have continued diversifying, developing ever more elaborate horns and frills. Perhaps some lineages would have evolved even larger body sizes, or returned to a more bipedal stance, or developed new defensive strategies. The hadrosaurs might have evolved more sophisticated vocalization, using their elaborate head crests in increasingly complex social communication. Perhaps some would have developed proto-language, sounds with specific meanings understood within their groups. The tyrannosaurs and other large predators would have continued their arms race with prey species, evolving better eyesight, faster running speeds, more efficient hunting strategies. Perhaps some lineages would have become pack hunters, coordinating their attacks the way wolves do. Perhaps others would have evolved ambush tactics using camouflage and patience, and intelligence. Could dinosaurs have evolved human-level intelligence? The question is fascinating and unanswerable. Intelligence evolves when it provides an advantage, when the problems an organism faces are better solved by thinking than by strength or speed or other physical attributes. Some dinosaurs, particularly the troodontids, had relatively large brains and may have been quite clever. Given another 66 million years, could one of their descendants have evolved intelligence comparable to ours? It's possible, perhaps even probable. Intelligence isn't uniquely mammalian. Birds, those living dinosaurs, show remarkable intelligence in many species. Corvids, crows and ravens and jays use tools and solve complex problems. Parrots can learn hundreds of words and use them meaningfully. These behaviours suggest the dinosaurian brain is capable of sophisticated cognition. Given enough time and the right selective pressures, there's no reason a non-avian dinosaur lineage couldn't have evolved similar or greater intelligence. Imagine a world where, instead of humans, intelligent dinosaurs developed civilization. They might have built cities, developed technology, contemplated their own existence. They might have discovered the fossil record and learned about their own deep history. They might have developed science, art, philosophy. We can't know what a dinosaurian civilization would look like. It would be shaped by their particular physiology and evolutionary history, but it's not impossible to imagine. And what of mammals in this alternate timeline? We would still exist, likely. The KPG extinction wasn't the only evolutionary pressure on mammals. We were diversifying even before the impact, occupying various niches. Without the extinction, we would probably have remained small and largely nocturnal, but we would continue to exist, perhaps even to slowly diversify and specialize. But we wouldn't dominate. We wouldn't have had the opportunity to radiate into large body sizes and diurnal activity. Primates might never have evolved, or if they did, they might have remained small tree dwellers, never giving rise to apes or humans. In this alternate timeline, there's no human civilization, no cities, no agriculture, no technology, no art or science or philosophy as we know it. All of human achievement, everything we value about our species and our history, simply doesn't exist. Not because we failed, but because we never had the opportunity to begin. This thought experiment reveals something profound about contingency. Our existence, and more broadly the existence of the world we know, wasn't inevitable. It resulted from a specific sequence of events, including a catastrophic asteroid impact that happened to occur 66 million years ago. Change any major event in that sequence, and the present changes dramatically. The asteroid missing Earth isn't a small change in initial conditions, it's a fundamental alteration of evolutionary history. Yet the thought experiment also suggests something about life's capacity for complexity. Whether dinosaurs or mammals dominated, whether intelligence arose in a troodontid lineage or a primate lineage or not at all, life would have continued, diversified, filled the planet with myriad forms. The specifics would be different, but the broad pattern, life's tendency toward complexity and diversity, would likely remain. Earth would still be a living world, just not the particular living world we know. Returning from our thought experiment to reality, we can appreciate how fortunate we are, in a sense, to exist at all. Not fortunate in a designed sense, there's no evidence the asteroid was guided or intended to create opportunities for mammals, but fortunate in the sense of being the beneficiaries of chance, of cosmic accident, of being on the winning side of an event that could easily have gone differently. The dinosaurs weren't fortunate, they lost everything. But their loss was our gain, and from that gain came everything we are. The dinosaurs are extinct, yes, but they left behind more than just fossils. They left legacies that persist to this day, influences that shaped and continue to shape life on Earth. Understanding these legacies helps us appreciate that extinction, while final for the species that die, isn't the end of their impact on the world. First and most obvious, they left behind the birds. Birds are dinosaurs, in the most literal taxonomic sense. They evolved from small theropod dinosaurs in the Jurassic period, long before the KPG extinction. When we watch a sparrow or a hawk or a penguin, we're watching a dinosaur. a living continuation of a lineage that stretches back over 200 million years. The birds carry dinosaurian characteristics: hollow bones, hard-shelled eggs, efficient respiration systems, bipedal locomotion. They're not like dinosaurs. They are dinosaurs, the only lineage that survived the extinction. This means dinosaurs never truly went extinct. They persist, flying overhead, singing in trees, wading through marshes, swimming in oceans. There are more bird species today than there were dinosaur species in the late Cretaceous. The dinosaurs in avian form are more diverse now than they were at their supposed endpoint. This is a comforting thought. In a way, the Great Catastrophe didn't end the dinosaurian experiment. It only redirected it, pruned it, forced it into different forms. The dinosaurs also left behind their fossils, and these fossils have profoundly influenced human thought and culture. When people first discovered dinosaur bones, centuries before they were recognized as dinosaurs, they inspired myths and legends. Dragon stories from around the world may have been influenced by fossil discoveries. Certainly, once fossils were properly identified in the 19th century, they captivated public imagination. Dinosaurs have become cultural icons, symbols of a lost world, representatives of deep time. They appear in museums, books, movies, children's toys. They inspire wonder and curiosity. For many people, including many scientists, early fascination with dinosaurs led to careers in paleontology, biology, or related fields. The dinosaurs, long dead, continue to influence the living through the stories we tell about them. On a more ecological level, the dinosaurs' extinction itself left a legacy. By vacating so many niches, they created opportunities for other lineages. The mammalian radiation, as we discussed, was a direct consequence of the dinosaurs' absence. The world we live in, dominated by mammals, shaped by mammalian behaviours and ecology, exists because the dinosaurs died. Our existence is part of their legacy. The dinosaurs also left behind chemical signatures in rocks. The fossils themselves, bone turned to stone, contain traces of original organic molecules. Scientists can extract and analyse these, learning about dinosaur biochemistry, their growth rates, their metabolic strategies. Eggshells contain isotopic signatures revealing environmental conditions. Tooth enamel records dietary information. Even the rocks between fossils contain pollen and spores revealing what plants existed, which in turn tells us about climate and ecology. At Chicxulub, the impact itself is the dinosaurs' monument. The crater, buried but still detectable, marks the moment of their extinction. It's a permanent scar on the planet, a feature that will persist for millions of years more. Geologists studying the crater learn not just about the impact, but about Earth's dynamic processes, about how planets respond to catastrophic events. The dinosaurs' extinction contributed to this knowledge, their terrible last day preserved in shocked quartz and iridium-rich clay. There's also a philosophical legacy. The dinosaurs' extinction, once we understood it was caused by an asteroid impact, changed how we think about Earth's history. We realised our planet exists in a cosmic context, that events from space can radically alter the surface. This awareness has influenced everything from our search for potentially hazardous asteroids to our thinking about planetary protection and the long-term survival of civilization. The extinction also demonstrated that dominance is temporary, that success is no guarantee against catastrophe, that life's history is punctuated by events that reset the game entirely. These are humbling insights. We humans tend to assume our current dominance is secure, that we've somehow transcended the forces that shaped earlier life. The dinosaur story suggests otherwise. They were more successful than we've been, ruling for over 160 million years, and yet they fell in a day. We should remember that. But perhaps the most important legacy is simply the knowledge itself, the story we've pieced together from rocks and calculations and careful analysis. The dinosaurs lived, evolved, diversified, dominated and died. Their story is one of the grandest in life's history, spanning vast time and affecting the entire planet. That we can know this story, that we can reconstruct their world and their ending, is a testament to human curiosity and scientific method. When we look at a dinosaur skeleton in a museum, we're connecting with deep time. We're touching a story that began before our ancestors existed, that ended before our ancestors evolved, but that shaped the world we inherited. The dinosaurs left behind more than bones. They left a story, and we're fortunate enough to be able to read it. That story informs us, humbles us, and fills us with wonder at the vastness of time and the persistence of life. Let's step back now, as far back as we can, and try to see the whole picture. The dinosaurs emerged about 230 million years ago in the Triassic period. They evolved, diversified, survived one mass extinction, and came to dominate terrestrial ecosystems. They reigned for over 160 million years, an almost incomprehensible span. And then, 66 million years ago, an asteroid struck, and their reign ended. In the 66 million years since, mammals have risen, birds have diversified, the continents have rearranged, the climate has cycled through warmth and ice. And in the last moment, the final seconds of this vast story, humans appeared. We've existed as a species for perhaps 300,000 years. Recorded history spans maybe 5,000 years. Compared to the dinosaurs' 160 million year reign, we're barely here. This perspective is worth sitting with for a moment. The dinosaurs had a run that was over 500 times longer than human existence. If Homo sapiens lasts as long as the dinosaurs did, it would be 159,700,000 years from now before we could claim equivalent success. That's a span so vast it's meaningless to contemplate. We might not last another 1,000 years, let alone millions. The dinosaurs set a standard for dominance and persistence that we're unlikely to match. Yet in our brief moment, we've achieved something the dinosaurs never did. We've become aware of the story. We know about deep time. We understand evolution. We can reconstruct the past and to some extent predict the future. We've developed science, art, philosophy, all the trappings of consciousness and culture. In our briefness, there's an intensity, a richness that purely duration can't match. But this awareness comes with responsibility. We know about the asteroid that killed the dinosaurs. We know about mass extinctions. We know that our planet exists in a cosmic context, vulnerable to impacts, subject to forces beyond our control, and we know that we ourselves are affecting the planet, changing climate, destroying habitats, driving species extinct. We're simultaneously the beneficiaries of past catastrophe and the potential causes of future ones. What should we do with this knowledge? The dinosaurs couldn't have prevented their extinction. They lack the technology, the understanding, even the awareness that an asteroid was approaching. They were victims of circumstances they couldn't possibly control or comprehend. We're different. We can see asteroids coming. We're developing technology to potentially deflect them. We understand the mechanisms of mass extinction well enough that we might possibly avoid causing one ourselves. This is both empowering and terrifying. We have agency in a way no previous dominant species did. Our choices matter on geological timescales. What we do in the next few centuries will shape Earth's ecology for millions of years. We could steward the planet responsibly, preserving diversity and complexity. Or we could trigger an extinction event rivaling the KPG boundary, a human-caused catastrophe that future paleontologists, if any exist, might mark as clearly as we mark the asteroid impact. The perspective we gain from the dinosaur story is fundamentally about humility and responsibility. Humility because we're so recent, so brief, so vulnerable to the same cosmic accidents and terrestrial catastrophes that have shaped all life before us. Responsibility because we're aware, because we understand, because we have the capacity to act on that understanding. When I think about the Triceratops grazing on that April morning 66 million years ago, going about her day with no knowledge of what was coming, I feel a profound connection across time. She was a conscious being, experiencing her world, living her life. She had no way to know her species would be extinct by evening. She simply was, in the moment, doing what millions of years of evolution had equipped her to do. We're not so different. We go about our days, living our lives, mostly unaware of how brief and contingent our existence is. We assume the world will continue as it is, that our species will persist, that the patterns we're familiar with will endure. But the dinosaurs probably felt that way too if they could feel such things. They were successful beyond measure, and then they weren't. They were, and then they weren't. This doesn't mean we should despair or abandon hope. Quite the opposite. It means we should appreciate our moment, brief though it is. We should marvel at the fact that we're here at all, that 66 million years of evolution after the catastrophe led to us, that we can understand the story and tell it. We should use our awareness to make choices that extend our moment as long as possible, and that preserve the richness and diversity of life that makes our planet remarkable. The dinosaurs had their era, magnificent and long. We're having ours, brief but intense. How long it lasts depends partly on luck, cosmic accidents we can't control, and partly on us, on the choices we make and the values we uphold. The story of the last day of dinosaurs teaches us that dominance is temporary, that catastrophe is possible, that life persists but in changed forms. It teaches us to be humble before deep time and to be responsible with the power our awareness gives us. And perhaps most importantly, it teaches us to appreciate the moment we have, because in the vast sweep of time, moments are all any species really gets. Thank you for staying with me through this long journey. We've travelled together across 66 million years, from the present day back to a single April morning, and then forward again to now. It's been 2.5 hours, a brief moment in geological terms, but a significant commitment of your time, and I'm grateful you chose to spend it here, drifting through deep time with me. We began with a mystery, the question of what happened to the dinosaurs. From there, we discovered a layer of iridium, traced it to a crater in Mexico, reconstructed a catastrophic day of fire and darkness, followed life's recovery, and ultimately found ourselves contemplating our own place in this vast story. From an asteroid's long fall through space to the mammals that inherited the world it shattered, we've traced a story that spans the cosmos and culminates in the moment we're in right now. The answer to our opening question, what happened to the dinosaurs, is both simple and profound. They were killed by an asteroid impact 66 million years ago, but that simple answer opens onto vast landscapes of understanding. We've learned about impacts and extinctions, about recovery and evolution, about deep time and contingency. We've seen that life is resilient but not invulnerable, that dominance is temporary, that our existence resulted from catastrophe and opportunity in equal measure. Perhaps the real answer isn't just that an asteroid killed the dinosaurs, but that catastrophe and creation are intertwined, that the world we know was built on the ruins of the world that came before, and that this pattern has repeated throughout Earth's history, and will likely continue long after we're gone. If you found some peace in this slow drift through geological time, if these contemplations about extinction and recovery helped quiet your day's noise, then please consider liking and subscribing. Your support helps these videos reach others who might need them, and to those who've been here before, who return to these long, slow explorations of time and space and life's grand story. Thank you. Your presence means more than you know, wherever you are in the world. Whatever space you've made for yourself tonight, I hope you're comfortable now. I hope your breathing has slowed to match the pace of our journey. I hope the worries of the day have faded into the background, made smaller by perspective, by the vast sweep of time we've contemplated. I hope your thoughts have quieted, or if they haven't, that they're at least peaceful thoughts, contemplative rather than anxious. I hope your body feels heavy and warm, ready for rest. Look up at the stars tonight if you can, if the sky's clear wherever you are. Imagine, if you will, all those points of light, each one a sun like ours, perhaps with planets orbiting, perhaps with life on those planets living its own story, facing its own catastrophes and recoveries. And imagine among those stars, asteroids and comets, rocks left over from the formation of solar systems, following their ancient orbits, most of them harmless, a few destined to intersect with worlds and change everything. We live in a universe that's vast beyond comprehension, old beyond imagining, and yet here we are, conscious beings capable of understanding our place in it. We're made of matter that was forged in stars, that cooled into planets, that organized itself into life that evolved for billions of years into us. We're the universe becoming aware of itself, however briefly, however locally. The dinosaurs were part of that same story, as were the trilobites before them, and as will be whatever comes after us. In the end, what the story of the dinosaurs' last day teaches us is that we're part of something larger and longer than ourselves, that our individual lives and even our species' existence are brief moments in an ongoing epic. But briefness doesn't mean meaninglessness. These moments matter to us, to the lives we touch, to the small piece of the universe we occupy. We can't control cosmic accidents or geological time, but we can control how we spend our moments, how we treat each other and the world we temporarily inhabit, what we create and preserve and pass forward. Sleep well tonight, knowing that you're part of this grand story, this 4.5 billion year tale of a planet's transformation. Dream, if you dream, of ancient forests and strange creatures, of cosmic visitors and the resilience of life, of time's vastness and the preciousness of the moment. Dream of dinosaurs grazing under unfamiliar stars, of small mammals hiding in burrows, of birds taking flight from branches, of oceans teeming with forms we'll never see again and forms we've yet to discover. Dream of asteroids tracing their slow paths through space, of planets turning, of life persisting and adapting and continuing its endless experimentation with form and function. And when you wake, whenever that is, you'll wake in a world that exists because of that asteroid impact 66 million years ago, because the mammals survived and the dinosaurs didn't, because evolution took one path instead of countless others. You'll wake in your particular moment of deep time, brief and precious, ready to add your part to the ongoing story. Good night. Rest well. Thank you for joining me in this exploration of the last day of the dinosaurs and the world that came after. May your sleep be peaceful, your dreams be gentle, and your tomorrow be full of wonder at the vast, strange, beautiful story we're all part of. Good night,